Go time. We're live. Want to talk? No. All right. So we're gonna treat this out to. Sheesh. We're gonna treat this um, like tree diagrams and show how this all works out, how it leads to what's called the. We'll get to that later. I don't want to jump ahead. You will be asked to make tree diagrams, and then in some you will just be asked to find a probability. I think I over treed first hour. I also assigned them all the questions, and they hate me. They're really mad at me. So I think at some of these, I'm going to stop at doing the tree. The tree just leads to why we do what we do with certain probabilities. Now, I will say this probably ahead of time, and hopefully I just can count this as review that you should already know this, but maybe you don't. When we use the word or, that is a rule in probability that you add. There's a very simple reason for this. As you write this down, hopefully you can do two things at once. Yesterday we asked, what's the probability of getting a face card or a red 2 or a 7? When I'm done with this, how many cards do I have in my hand? Do I have 3 or do I have 1 card in my hand? Yesterday's assignment. It was 1. You were drawing 1 card. We just want to know the probability of it being this or this or this. And what we did was add those 3 probabilities of each individual event together. But in the end, it was just the probability of that 1 card being one of those 3. Today, if I ask that same question, what's the probability of getting a face card and then a red 2 and then a... Put that phone away, sir! Oh, it's gum. Sorry, internet. I freak out when people grabbing, reaching in their pockets. You never know what's going to happen there. All right. What was I saying? Face card and red 2 and 7. How many cards do you have in your hand at the end of that statement? And means I have 3. And then you're going to find out to actually do that probability. Not really complicated. You got to worry about what are the circumstances, but what you do is multiply those probabilities as you come across. And that's what the tree branch or the tree diagrams will show you. So the next thing, like I yelled at you, too bad if you don't have this all written. I wouldn't take it all down anyway. This will be emulated. This is the words that will be emulated in what I snagged right out of the book again, Lazy Mr. S. I couldn't care less what people say about me. All right? So here's the example. Not really written in an example format, but in a pictorial format that I stole from the book. We're going to choose how many marbles? What does it say right there? 2 marbles from 1 red, 1 green, 1 yellow, and 1 white are the ones that exist in there. Okay, well, here's the scenarios that could occur. And again, when you have to construct a tree diagram, and many were able to do this first hour while I was blabbering, just so you know what it is, these are what could happen. You could choose red first, or you could choose green first, or you could choose yellow first, or you could choose white first. These are the first 4 possibilities. But then after you choose red first, how many marbles are left in the jar? 3. This is with or without replacement. Now you better read the book. Is this with or without replacement if there's only 3 marbles left? Without. You're not choosing a red marble, then popping it back in the jar, and then re-choosing, which is a scenario we could lay out. But we're not replacing. So once I get the red, then the next scenario, there's only 3 possibilities. You could choose green, yellow, or white. Or if we first got a green, then the next possibility would be choose a red, a yellow, or a white. And so on and down the line. When you go to the end of each of these branches, these are all of the possible outcomes of choosing 1 marble and then choosing the next marble without replacement. How many possibilities are there? There's 12. Well, it's not any coinkydink that the first scenario, how many possibilities were there? How many possibilities were there in the first scenario? How many possible marbles can I choose from? Everyone say the number. 4. But then after you get that marble and don't replace it, how many possibilities are there for each of these scenarios? 3. What's the relationship between 4 and 3 and 12? What can I do with 4 and 3? Multiply them. So that's why What's the probability of getting, or how many ways can we get when we how many possible scenarios, let's say, try and say in probability when this isn't probability, it's just how many ways. Can we choose one marble and then another marble without replacement? There's 12 different scenarios. 4 times 3. So now, stretching? No math pulled muscles. Believe me, I know how that is. Whew. Okay, so this leads to the fundamental counting principle. This is a bunch of rigmarole. If an event or action A can occur in R ways and B can occur in S ways, the number that both A and B can occur is R times S. Multiply. So that's just a long way of explaining what we just went through. You have 4 possible choices for the first marble. After you pick one, you only have 3 possible choices for the second one. There's 12 total ways that this could happen. Then this turns into what we're going to do for probability. These are just how many ways. You know, probability is put it in a fraction format. Okay, this is all I have. I have 3 shirts, 2 pairs of pants, and 2 pairs of socks. Okay, so how many different outfits can I, can I walk out? Where? I don't know what happened there. Right? Walk out the door with. Okay. Now, if they ask you to do a tree, do it. I may do this tree and then one more, and I'm not really good at these. I'm going to be honest. But the first thing you can choose, and it doesn't have to go in any order. This isn't that lesson where I taught you how to put your clothes on last semester. Okay, so shirts. And then I didn't put them color coded. I remember when I did this in Algebra 2, we color coded them. Like I have a green shirt, a purple shirt, and a pink shirt. All right, so I could choose either this shirt, or this shirt. Then after I choose this shirt, I can choose a pair of pants, which I'll make that a different color. Pants. And then I've already gone too far because I have to add socks to that end there. So pants. I choose this shirt. Now I could choose any of these 2 pants. And I could choose any of these 2 pants. And you can see I'm not very good at drawing these scenarios. Then after the pants, I pick those. I don't know how I can make this better for myself. Then I could choose from any pair of socks that I have, and I have 2 sets of those. And you're supposed to label these, and obviously the bigger the tree gets, what? The harder what? It is to what? Fit on a piece of paper, draw neatly and nicely, and I'm doing a horrendous job with my limited writing abilities. You can at least see at the end of this, and again, if I were to color-coded the shirts, say shirts were, as you write this down, what did I say? Purple, blue, and green? I didn't say that. This is purple shirt with black pants with white socks. That'd be a good-looking guy. Purple shirt, green pants. No, I missed that. Sorry. Purple shirt. Well, I forgot the colors. You know what I mean. You get what I'm saying. These are all different outfits if you follow each line differently. How many different outfits can I walk out the door with? 12. Sorry. 3 times 2 times 2. 3 possible shirts to choose from, 2 possible pants, 2 possible socks. Okay, so like I say, the tree diagram just designates and shows you how this ends up occurring, what you end up having possible outfits for if they have this occurring. She just threw hers. All right, so now, so you make sure that you know what cards are. A standard 52 deck of cards is what they use. Didn't they talk about a pinnacle deck yesterday? Was that in yesterday's homework or is that today's? I think that's today's. Don't worry about it. They tell you what a pinnacle deck has, and it's different. It's a different game. It's not Pinochle when you read that. Pinochle. Anyway, suppose 2 cards are drawn. So what we have to say is we draw the first card, and then I draw a second card. So how many ways can I get the first and the second that we're asking? Don't write this down. As a matter of fact, it would be nearly impossible to write all of what they show you here. This just shows you the this principle, the fundamental counting principle, is how this lines up. So here we go. Oh, on the left is all possibilities of drawing 2 cards. See, and this is why this is ridiculous. How many cards are there? So I have 52 to choose from. So I could either choose the ace of spades. After I choose the ace of spades and I don't replace it, how many cards do I have to pick from after that? 51. So I could choose the ace of spades, then I could choose the next card. The ace is gone, so could I have the king, queen, all the way, all the spades, all the hearts, all the... So this would be a tree of 51 branches right here. Would that be easy to draw, yes or no? That's why they dot it. Or I could choose the king of spades first, then the next card I could choose the ace. Now this, when they say you choose a card, then you choose another, you do count choosing ace first, king second, different than king of spades first, ace of spades second. This is what's tough about probability. We're going to have to really hammer in your head when order matters and when it doesn't. So obviously we have how many lines here if I completed this first stage here? 52. How many lines come off of each after the first scenario happens? 51. When we're doing probability, we know that is the denominator. The denominator for finding probability is divided by all possible scenarios of drawing 2 cards. Now, I probably didn't give you enough time to write what the question was. Find the probability of getting a pair. I really like how the book does this. This is why I yanked out the things that they put in there. So, what is a pair? If I grab a 2, what's my next card got to be? A 2. A pair is 2 of the same cards. So, what are my possibilities on the first card? How many cards do I have to choose from on the first card? I could still pick any of the, say it. Got some people rambunctious back there. 52, right? I don't know if you guys said that, but it's common sense. I still have 52 to choose from in the first pick, but now we're stuck. We're stuck. Now that I picked the first card, what must I pick in order to get a pair? Well, if I pick an ace first, what do I have to pick next to get a pair? Another ace. How many are left after I pick an ace? 3. There's 3 aces left after I pick one of them. Repeat myself. So on the second line, if I get an ace first on one of my first 52 picks, I only have 3 possibilities to complete the pair on the second pick, no matter what I got on the first pick. So the numerator, or how many ways can I get a pair, 52 choices on the first pick, only 3 on the second to complete the pair. So this is how you compute the probability of getting a pair. The amount of ways you can get a pair divided by the amount of ways you can choose any 2 cards and have that unique. By the way, how is this easy to simplify? What can I do right away without, using a calculator? Cancel the 52s. Then understand what 3 over 51 is. What's 3 over 51? 1 over 17 if you know your multiplication tables. Then you can turn it into a decimal or a fraction. Okay? Okay. Now the next thing. You don't have to write all this down. All this says is, instead of putting how many ways on the tree that we're drawing, we can actually put the probability of something happening on a branch. And then do something with those probabilities. This is called a probability tree diagram. And then I came up with one that's a little bit unique, and then a little bit more, the next one's a little bit more complicated. Darn, I gotta hide something here. Let me just do something for a sec. Okay, we're on. Okay, here we go. Actually, the video shows, but the class does not. Boom. This doesn't quite, well, actually, let's just read it. Okay, so I pulled a drawing and their example out of the book and then wanted to put my own writing. A lot of times, too, when I look at the book, they really explain it, but sometimes it's overdone, maybe a little bit, and I try to shorthand. If you want to go to the book and read it, that's good as well. Draw a probability tree for the experiment of spinning the spinner. Okay, and then you should know something very simple geometrically. But let's analyze the question. And I did this on purpose because I wanted to, disseminate between these two words. Determine the probability of spinning a lander on W or G. How many times am I spinning? Once. They just want to know in the one spin, what's the probability of getting W or G? Apparently, spinning a spinner is hilarious. Fifth hour. Okay. First of all, you need to understand that the probability of landing on white or green is what this stands for, is the union of white or green, which is actually finding the sum of those two probabilities because I'm only spinning once. I just want to know in this one spin, what's the chance I would land on W or green? Okay, so, but I got that in the way. I got to move this. Yeehaw. Yes. Now. That's a G, yeah. Okay, now. You could either land on red. I'll color code this. By the degree measures, if you can see them. It's a little dark in here, I guess, or not dark enough, actually. It's 90 degrees. So what's the probability, geometrically speaking, I land on red? You better know that a full circle is how many degrees? This is not rocket science. If 90 degrees is there, what's the fraction? You have a 1/4 chance of hitting red. This is a probability tree diagram. So what I'm going to do the rest of the notes when even it gets more complicated. Let's go to the green next. What's the probability of hitting the green? If you can see the angle measured is also 90 degrees. Yellow is going to show real well. Here's yellow. Can you see it? Okay, what's yellow's probability? Ooh, that's 60. So what would that be? 1/6. Okay, that looks horrible. All right, you know what I'll do? I'll highlight it in black. That worked. Never mind. Okay. All right. Maybe if I highlight it after the fact. Okay. And then what about white? Oh, what about if you hit the white one? What's 120 out of 360? 1/3. And then we'll stop at the colors because this didn't work out very well. Okay, so now you should understand this is not an and, this is an or. Don't get tripped up when they switch up the game on you. You want to find the probability of white. The probability of white is 1/3 plus the probability of green, which was 1/4. And I'd be infinitely sad if you went to the calculator to figure out what that answer was. 7/12. And then you can change that into a decimal or a percent. All right. Only in this one, and plus it's because I'm horrible at it, and I need probably more space than I gave to you. Only on this one will I draw the tree out. But you got to really be careful, okay? Because this is actually in a way called conditional probability, where if this happens, then what do you have as your selection next? Okay, so, and I did it, and it kind of worked out okay, except the drawings are tough. 2 different questions in one. The idea of with replacement and without replacement. So, made it simple. The question is that we're drawn from a gumball machine. There's 3 red and 2 green. You can see them. You're not blind. Okay. Computing multi-stage probabilities with replacement without. Drawing 2 gumballs one at a time. What is the probability you get 2 green gumballs? If they ask you to do a probability tree, then this is what you got to do. You have choice 1. I guess I'm going to try going, you can go horizontal or vertical on these. Doesn't matter. 2 possibilities. In the first choice, you could either get what? Red, or you could get what? Green. Son of a nutcracker. This thing just does not work for me. What's the probability of getting a red on the first choice? 3 out of 5. Therefore, what is the probability of getting a green on the first choice? Now we got a problem. Now we have a second choice. We have 2 lines of possibilities. We have to consider that. And I can only say it, I can't write it because I can't fit it on here. If I get a red gumball first, How many red gumballs do I have for the second choice on this line? 2. How many green do I have? 2. So, on the second choice, what is the probability of getting red again? 2 out of 4. There is only 2 reds and 2 greens if a red is picked first. I can't write it. I tried to write it first hour. It did not go well. So we're assuming this red ball is picked. Then for the second choice, without replacement, I only have 2 reds and 2 greens. So therefore, what is this probability on this branch?
1/4.
I still don't have it. 1/2. There is 2 greens and 2 reds if 1 red is picked first. Did I say good afternoon? Yes. Okay, now I pick a green ball, and I got it in the first choice. Now everybody, here, I'll put my hand up. Here, I'll do this. Okay, so if I'm on this line, this is gone. Count the balls. There's 4. 3 of them are, and 1 of them is. So what is my probability on the next choice that I get a red? 3/4. And then what is my probability I get a green? 1/4. You did that on purpose, I hope, Jin. So now you follow the line of logic, or you follow what I wanted to have happened. And I wanted to get 2 green gumballs. So do I go this line? No. I want to go this line. I got green on the first, then green on the second. So the probability of getting a green on the first without replacement and then green on the second is 2/5 times 1/4. Cross cancel, 1/10. Then like I said, this tree will actually be used for the next one because the next one says drawing 2 gumballs. These are all the scenarios that could happen for drawing 2 gumballs. But now we're going to follow a different line. What's the probability of getting a red first, then a green? We can answer that later. Let's do the tree real quick with replacement, which actually is a lot easier. Okay, with replacement, what's the probability of getting a red ball on the first choice?
3/5.
What's the probability of getting a green ball on the first choice? In either scenario, I throw the gumball back in the thing. In my second choice, what's the probability of getting a red? 3/5. You threw it back in there, you got 3 reds and 2 greens again. With replacement just means resets the whole setup and you do it again. What's the probability of getting a green ball? 2/5. If I get a green ball and then replace it, what's the probability on the second choice I get a red ball? 3/5. With replacement is easy. Without replacement, you have to think what's left over for the second choice. And then, of course, this one said, what's the probability of getting a green gumball and then another green gumball? 2/5 times 2/5, which is 4/25. All right. Now, what I'm going to do for this, I'll do it offline. So for the next example, since I made it identical, drawing 2 gumballs one at a time, these are all the possibilities that this could happen. You could get red and then red, red and then green, green and then red, green and then green. And those are the probabilities of those happening without replacement. Now all I care about is red first, yoink, green second, yoink. And then red first, green second, with replacement. 3/10. Nothing cancels, 6/25, and you can turn it into a decimal or a fraction. I am not drawing the tree out. Actually, poor first hour who had to do all their homework instead of odds, and also had to watch me try to draw this. It didn't work out, so you're just going to have to pay attention and think about it. Okay, without replacement is the toughest, but we have to figure out what we have left over. What is the probability it takes you exactly 3 draws to get a red gumball? What does that really mean? I have to get what first then? Green. What do I have to get next? And then what do I have to get next? Those are not R's. Or, I'm sorry, 6's. Those are green, green, and then red. So, what's the probability on the first draw that I get a green? Everyone should know this. 2/5. Now we're going to do it like this. It seemed to work out for those that are half paying attention every once in a while. Without replacement, that green ball is gone. So what's the probability of getting green again on the second choice? 1/4. Then, oh wait, I forgot. I'm sorry. That's gone. What's the probability of getting a red on the third choice? 3/3, or 100%. So the probability of getting green, green, then red would be 2/5 times 3/4 of 1/5, right? According to my math, cross-canceling. 1/10, according to my bad math that I was never good at. Okay? Now, with replacement, very simple. What's my probability of getting a green on the first? Huh? Oh, dear. 2/5. I put the gumball back. Some people are chewing on the gumball vigorously. 2/5. You put it back. You put it back again. What's the probability of getting a red on the last one? Only 3/5. Because we have the 2 back in there. So that's why that one gets reduced. So you don't need the tree to actually figure it out, but you need to figure out with or without replacement what's left, what's not. Let's look at what someone's looking out the window like something great's happening. Now I'm curious. Oh, you know what it is? Oh, it's still going. Okay. Playing this because it seems like a random thing. Uh-oh. To just kind of talk about, but okay. I asked this question first hour. They probably already hated me at this point, and everyone didn't raise their hand. But did anyone ever see the Moneyball movie? Moneyball? The movie Moneyball? Baseball? Okay, and it's all about how statistics are used in baseball, and actually in all sports, is what it's used to, track things and see possibilities. So somebody was watching this. Just go along with it. That the LTHS volleyball team serves first somehow in 67% of the games. So throughout the season, this is what's happened, somehow. And then it's been noticed that they win 72% of the games in which they serve first. But only 23%, obviously, in which they serve second. Find the probability that LTHS will win any randomly selected game. Whoa. Because they either win or lose. That is a 28. Fine. Okay, now you're done. No more comments. But you're right. It should be 28 and 72 that add up to 100. Either win or lose. Is that word okay? You just rolled your... So the student threw me off. So again, you're canceled. Go sit in the corner. All right? So if you win 72 when you serve first, you lose 28%. But when you serve second, you only win 23%, but win the other of what's left over. Was that I was never good at the 77, right? Okay. Now, this is what you got to do. You could either, when you go to a game, serve first or what? Serve second. So that's the two possibilities to start off. And if you serve first, you can either what? You can either lose or win. If you serve second, you could still win or you could lose. So this is what you have to set up based off of the probability situation we were talking about. You could go to a game and you could either serve first or serve second. If you serve first, you serve first 67% of the time. You serve second 33% of the time. Somehow this happens. You must be good, lucky coin flippers. I don't know how they determine how you serve first or second. Then if you serve first, you could either win. When you serve first, the probability of you winning is 72%. Therefore, the probability of you losing is 28%. So you could serve first and win, serve first and lose. Or you could serve second and win. When you serve second, you only win 23% of the time. Or serve second and win, or lose, you lose 77% of the time. So I think I said that wrong. If you serve second, that's 33% of the time, and you could win, which only happens 23% of the time. So for some reason you don't like serving second, it really throws your team off. Boom, boom, boom. Actually, I think that happens in volleyball anyway. When you serve, you have a better chance of winning. Whatever, let's not overanalyze it. So what's your probability of winning? Probability of serving first and winning? Or probability of serving second and winning? That means you add these two probabilities. So you could serve first and win, or you could serve second and win. Did you notice how annoying I was saying that? Because I was emphasizing the words what? And, or. Then you go ahead and multiply these and add them, and you could do that. We'll do that offline as the last one. Very similar scenario pulled out of the book. Two things that are completely different and actually change the scenario. Jar contains 3 balls, 2 green and 3 red. I'm sorry, 3 red and 2 green, so 5 balls total. First, the coin is tossed. Shh. If the coin lands heads, a red ball is added to the jar. If a coin lands tails, a green ball is added to the jar. In the second step of the experiment, a ball is chosen from the jar. What is the probability that that red ball is chosen? So this is a crazy one. It seems difficult, but it actually is not. What do you have to do first? What do you have to do first? Toss a coin. You either get heads or tails. If you get heads, what do you do with the jar? You add a red ball. So now instead of 3 red balls and 2 green balls, you have 4 red balls and 2 green balls. So that's what this line represents. You have a 4/6 chance now of getting a red ball and a 2/6 chance of getting a green ball. Okay? And then basically what you do, we'll talk about that later. Or what could happen is you could choose tails, and in that case you would add a green ball. So therefore, if you did tails, you'd have a 3/6 chance of getting a red ball and a 3/6 chance of getting a green ball. The question asks, what is the probability a red ball is chosen? 2 things could happen. You could roll heads, then choose a red ball, right? Or you could roll tails, then get a red ball. So this probability is 1/2 times, we should reduce 4/6 to 2/3, or 1/2 times 1/2, which is what 3/6 is. And then it's the sum of those 2 probabilities that ends up being what would be the possibility of getting a red ball. So before this even happens, this is the probability of flipping a coin, adding balls to the jar, then getting a red ball after that. Just like the volleyball example. Okay?